So we have Andy Palmquist here today from Western Ontario. He's a National Senior Fellow. Completed his PhD at the University of Victoria in 2013.
I think so, yes.
Then took a postdoc at the University of Leeds, followed by another postdoc at the Max Planck Institute for Extraterrestrial Physics in Germany, and is now back in Canada. So today we'll be talking about protostars and superbubbles.
Hi, thank you. So yeah, it's always good to be back here at CITA. It's always nice to be able to give a talk for you guys since you are paying half my salary, so it's much appreciated. So today I'm going to be talking about two separate research projects that I've been involved with. I've got a few other ones on the go as well, but I wanted to talk about these two. Both of these are in collaboration with other people, so a lot of the work that I'm going to be showing today is going to be work done by others. It's not necessarily mine, but I wanted to at least advertise a little bit for these projects. So the first project I'm going to talk about is JCM Load Program. It's the transient search for variable protostars. It's one of the very few load programs that we actually don't have an awkward acronym for. We just refer to it as the full title. This is a load program, so about 100 researchers on it, lots of East Asia collaborators, UK, Canada. PI is Greg Hertzig, co-PI is Doug Johnstone, and I particularly want to point out three graduate students, Steve Mayers, James Lane, and Hinju Yu, who have been doing an amazing amount of work on this project and have done a lot of the calibration work and the pipeline work so far in the project. But before I go too far into the project, I want to take a quick step back and talk a little bit about protostars and why it's interesting to actually do this sort of survey. So to form a star, we start in a molecular cloud. Molecular clouds are clumpy. And when you have a particularly dense, gravitationally bound bit, you've got a prestellar core. These cores will collapse in on themselves and eventually form a hydrostatically supported object, which is the protostar. The earliest stage of the protostar is the class 0 object. At this stage, there's more mass in the envelope and core around the protostar. There's less mass in the protostar than its surroundings. At this point, pretty much all of the light from the protostar itself gets absorbed by the envelope, reprocessed by the cold dust, and thus the SED that you get at this stage is pretty much all out in the submillimeter. There's very little visible emission, if any, and we're seeing a peak sort of 450 to 800 microns out into the submillimeter. The next stage is the class 1 stage. This is when the protostar has gained more mass than the envelope. At this stage, it's also driving outflows. It's probably opened up a cavity. So we're seeing some photons directly from the protostar, but we're still seeing a significant amount of emission from the surrounding envelope. So you start seeing a few shorter wavelength photons, but you still have quite a bit of emission coming from the submillimeter from the envelope. As time goes on, the envelope eventually disperses until you're left with just the protostar and its surrounding disk, at which point it becomes a class 2 protostar. At this point, you'll see the photosphere reasonably nicely, but you'll still see a significant infrared excess because of the disk. And eventually then the disk will disappear, giving you your class 3 protostar, where it's pretty much just the photosphere emission. It's still protostar at this point because nuclear fusion has not started in the center of the star. The star still has to contract a little bit more and heat up a little bit more before fusion starts. It's key to note that with protostars, there is no nuclear fusion. The power source is entirely from gravity. That, in fact, the luminosity that we see can very easily be related just to the accretion luminosity of material onto the protostar. And so we can write the accretion luminosity very simply as the gravitational constant times the mass of the protostar times the accretion rate divided by the radius of the protostar. We've got a pretty good idea what the radius of the protostars are, about a solar radius. They might be a little bit more bloated. And the mass of the protostar is very well constrained since we know what the IMF is. We know what they can get up to. But it's the accretion rate which becomes a very interesting question. Theory tells us what the core's density structures should be, or at least the first level of the theory. And if you then predict how that sort of core structure will collapse, theory predicts that you should get a constant accretion rate of about speed of sound cubed divided by the gravitational constant. And so this would then predict that if the mass accretion rate is constant, the radius stays reasonably constant, then the luminosity should just scale linearly with the mass over the lifetime of the protostar. However, there's a significant problem when theory meets observations. When we go out and look at how bright protostars actually are, we find that they're much dimmer than you would expect for this constant mass accretion rate. What I'm showing here is the bolometric luminosity of the protostar on the y-axis, the temperature on the x-axis, so the youngest objects are on this side, the oldest objects are on this side. And then the shaded colors here is where you would expect from theory to see protostars based on a constant accretion rate. All of the points are what we actually observe when we go out and observe the luminosity of protostars. And what you can see is that we are drastically underestimating the vast majority, we are overestimating the luminosity of the majority of protostars. The protostars are too dim. There's a few protostars that agree with the theory. There's even a few that might be a little bit brighter than predicted. But by far, most of the protostars are too dim for this constant accretion rate. Now, we know that over the lifetime of a protostar, the average accretion rate has to be roughly this c cubed over g value. We know how quickly protostars form. We know what their final masses have to be. We know what the average should be. And so this is a real problem that it's even referred to as the luminosity problem of star formation, that the protostars just seem to be too dim. So one possible solution to this is maybe we don't have steady accretion. Maybe we have protostars gaining most of their mass in large bursts, such that the majority of the time they're accreting at rates below their time average. And then for small bits of time, they accrete at very, very high rates. And thus, you would expect to have fairly high luminosities for those short durations of their evolution. There are theories of MHD disks that can predict this sort of bursty accretion. This is one model by Vorobayov. I'm probably butchering his name, so my apologies if he's watching this on YouTube. This is one of the models of the mass accretion for the MHD disk, where you can see there's these large accretion bursts. My apologies, gravitational instabilities. I think they have, do they have the MHD disk maybe, but okay, yes, my apologies. And so with this sort of episodic accretion models, usually we can lower most the accretion rates, and so we can get reasonable agreement with the models. So the question becomes, do we actually have observational evidence for this sort of episodic accretion? And the answer is we do. We do have some signs that we have it. So for instance, in the older objects, the class 2 and class 3 objects, we see significant variations in the optical magnitudes of some of these stars. We have a few different classes. For instance, you have FU Ori and X Ors. So the FU Ori is characterized by definitely a few magnitude jumps, but they tend to stay high in the burst mode for decades. So you're looking at gravitational instabilities in disks, whereas things like EX loop, which was an EX OR type, has about a few month long burst. For the shorter time scales, it probably has something to do with more the inner disks, so potentially magnetic instabilities for those objects. However, the class 2 and class 3 objects are objects that have already gained the majority of their mass. These are objects that are just accreting the last little bits of their mass. And so we'd like to know more about what's happening in the earlier stages when the stars are still gaining most of their mass. We also have evidence, if we look at outflows, that in the protostar stage you get these very powerful bipolar outflows. Typically speaking, we believe that the rate of flow in these outflows is proportional to the rate that they are accreting. So when we see these sort of knots and structures in outflows, one interpretation is that this is tracing accretion bursts, where we see more mass in outflow corresponds to an era where there was a higher mass accretion rate. However, is definitely possibilities that if you have a variable speed outflow, if you have structure in the interstellar medium that it's being driven into, there's all sorts of ways that you can create structure in these outflows that's not necessarily related to the mass accretion rates, but it's still plausible that this is a sign of episodic accretion. With ALMA, we've seen lots and lots of structures within disks that we see spiralomes, we see clumps, we see gaps opening in rings. And all of these structures suggest that you're going to have time variable accretion rates. That if you're going to have a constant accretion rate, you would expect to see a reasonably smooth axisymmetric disk. That all of these structures within the disks are all features that could potentially lead to time variability in the accretion flow onto the protostar. And we also see signs of chemical from the chemistry. That looking around some protostars, we see evidence of molecules still in the gas phase that really shouldn't be there given the current luminosity and the current temperature of the gas. That they're usually interpreted as being signs of a previous burst of accretion, a previous increase in the luminosity, and thus an increase in temperature surrounding the protostars. But all of this is pretty much evidence for the later stage accretion or its indirect evidence. That there's very little work that's been done on the time variability of the earliest stages of protostars. In fact, that it was only really in 2015 that we really saw the first evidence of a nice time variable class 0 protostar. And so part of the reason why this has been so tough to study is that if we go back to our SEDs, that if we want to study the earliest phases, the class 0 and the class 1 phase, they're so deeply embedded that we can't be using the visible light. We need to be going into the sub-millimeter. We need to be using tools like the JCMT to be able to actually observe these young protostars. And so that's basically the motivation for the survey that we're doing. That this is a large program on the James Clerk Maxwell telescope, so it's sensitive to 450 micron and 850 micron emission. We can actually observe both wavelengths simultaneously with the Scuba 2 instrument. And with this large program, we're going to be observing 8 roughly 30 arc-minute patches of nearby star-forming regions. And what we've got in time to do is for the next 3 years, or I should say for the next 2 years plus the previous year, we've been observing for about a year now, we're going to be observing each one of these regions roughly once a month. And we're basically going to develop this 3-year light curves for hundreds of protostars to really get at the time domain of what's going on with the time variability of all of these protostars. And I should quickly point out that this periodicity of about a month with our observations is partly set by the photon travel times within the envelope. That even if you were to instantaneously have a burst of luminosity in the protostar, because they're deeply embedded and all we're seeing is the reprocessed light, it takes about a month for the total dust luminosity to ramp up for that emission to thoroughly heat the dust, and for that emission then to make its way through the envelope to us. And so things tend to get smoothed out a little bit because of this dust reprocessing timescales for the youngest objects. So the 8 regions that we're going to be observing, or are observing, are these 8. So OMC, NGC 2024, NGC 2071, Ophiuchus, NGC 1333, IC 348, Serpens Main, and Serpens South. So Ophiuchus, Perseus, Serpens, Orion, all sort of the big classical well-studied nearby low-mass star-forming regions. For my role in this particular large program, I'm the Ophiuchus region team lead. So it's my responsibility to look at the Ophiuchus data every time it comes in, make sure it looks reasonable, see if there's anything super obvious in the data, and then to start implementing a pipeline to go through the data and see if I can actually find signs of variability. We've got different people becoming the leads for the different regions, and we've got a few different pipelines in the works with the idea that we can then share all of our pipelines with each other, see what works on which sets of data, and hopefully iterate until we've got our preferred pipeline. But it's still very much in the early stages where we've got multiple pipelines under construction. But one thing I should point out, so with these 8 regions, we've got about 250 protostars between all of them, over 1,000 disk sources, because we can still see the disks in the sub-millimeter. And while we're going to get some amazing time domain data, we're going to get really the first great 3-year study of these class 0, class 1 objects. I should also point out that when we stack all of this data together, at the end of the 3 years, we are going to have the deepest sub-millimeter maps of these regions by a factor of about 2.5. So at the end of these 3 years, any science that you would want to do with your typical single epoch image of these regions, you're still going to be able to do, and you're going to be able to do it better, because we'll be able to go deeper, or at least with better signal to noise on the objects that are there. So a lot of great science. We've got time domain, and we can do all of the single epoch science that you would normally want to do with this sort of continuum emission.
It's actually, when you say 250 protostars, you're talking about things that are only seen in the submillimeter and not infrared detections or something. What's a protostar?
To be quite honest, I grabbed this slide from somebody else, so I'm not entirely confident how they tallied that.
Okay. So using the Spitzer catalogs that were assembled for all the gold belt regions?
I think some of it is Spitzer. For the disk sources, I think there's been some of the previous surveys as well for embedded objects. I think the Herschel, they grabbed stuff from the Herschel. This was Scuba 2, so there's been the original Gould Belt survey that did a lot of this work. So it's been going through the catalog.
Deeper, so you might discover other.
Yeah. We're getting, at this point, we're getting pretty close to the current level of the Gould Belt survey, but we haven't gone a whole lot deeper at this point. So we are hoping to be able to go deeper, but at this point, we know of about 250 within these regions. But we definitely hope to be able to go deeper and pick out all sorts of faint little things. All right, so I want to quickly go over a little bit about what we're actually doing with this data, because we've got about a year of data so far. And so a lot of our efforts so far have been into developing a good pipeline and finding good calibrations of the data to make sure that we can pick out when a transient signature occurs, and we can be confident that it's actually a transient signature and not just noise in the data causing variations. So the first calibration that we're having to do is just to align the different maps that we have to each other. To do this, we're using a cross-correlation technique. So what we're basically doing is we line up the images, we multiply all of the same pixel locations together, sum all that up, get a sum, and then you shift the array over by a pixel, do that sum again, and you keep doing it until you can maximize that sum. With the idea being that when you have peaks, the biggest product is going to be when the peaks line up. And so if you've got bright sources, when you can get those lined up, you should maximize the cross-correlation. And we're actually finding quite a bit of success. We're finding that this sort of procedure can get us alignments to within about 0.03 arcseconds, or about 1/100th of a pixel for this. So we've been very, very happy with the spatial alignment. The bigger question for calibration, though, has been flux. Because we're interested in the variability of the protostars, we'd love to get a really good relative calibration between the different epochs of images. Intrinsically, the JCMT has about an 8% calibration, but we think we can do better with our own images, because most of the sources on our images won't be time variable. But most of them we expect to be fairly constant. And so what we want to do is, assuming that most of the values stay the same, we want to be able to calibrate each image across each other to try and improve the intrinsic calibration of every point. So what we do is we first search through all of the images to find all of the bright sources, so ones above 500 millijanskis. And ideally, we want to have fairly isolated sources, ones at least that are not confused with other sources, so we can get a really nice measurement each time. And we want to make sure that they appear in all of the epochs. What we then do is for each source, we calculate their average brightness over all of the epochs, and then we normalize everything. So we basically want to say, is it 3% brighter than normal? Is it 3% dimmer than normal for each of the images? What we can then do is then we can take the ratio of these normalized brightnesses between pairs of sources. The idea here is that if it's just a calibration issue, and we screwed up the calibration and everything's 3% brighter, then by taking the ratio of the normalized brightness, that should get everything back down to the same ratio, that the ratio shouldn't change if it's just a calibration issue that's uniform across the field.
Are you just going to use pairs? You think you'd use all stars with the same flux?
Getting there. And so just as a quick example of this, if we take these two, this is the Ophiuchus region, by the way. If we took the two isolated sources, measured their brightness, divide by the average to get a normalized brightness, we can then look at the ratio. And so for these particular ones, we could say, all right, the ratio seems to be reasonably constant. So it looks like in epoch 1, we just messed up the calibration and all the sources seem to be about a little bit brighter. Epochs 2 and 3 seem to be a slightly fainter epoch, that everything got reduced a little bit. And epoch 4 seems to be about right. And so what we can do is for a particular pair, we can look across all of the epochs. And ideally what we'd like is for the dispersion in this ratio to be less than 6%. That was the threshold that was chosen by the team based upon the intrinsic calibration accuracy that we think we're getting from the JCMT to begin with. That we trust anything within about 6% to be varying similarly between everything. And so what we do is we then try and find the largest group possible of these bright compact sources where every single possible pair of that group shows a scatter less than 6%. So we're basically trying to find the largest group of sources that seem to vary in the same way between all of the different epochs. And ideally this means that these they should match, because hopefully they're not changing and it's just the calibration that's changing, which is why they're all changing the same. And so what we're doing is we're just trying to find the largest group possible rather than picking out a particular two. So hopefully that answers your question.
Well, I also want to match them in flux, right?
Yeah, so that's why we set the 500 millijansky limit, which is...
So it's usually divided into either yes or no.
Yeah, basically. Anything that's reasonably bright that we have confidence in, such that we have good signal-to-noise detections. I think it's about a signal-to-noise of about 50 is, I think, where we set our threshold. And then basically what we can do is with this calibrator family, ones that we think is constant, is we can basically find what their typical normalized brightness is in a particular epoch and say that's how we need to change our calibration. And so we can divide out all of the other sources by this normalized brightness to get our best calibrated intensities. So again, going back to our example, if this was our calibrator set, if we only had 2 stars, yep.
It's a bolometer.
Yes.
So it is linear. It's a linear detector.
I think so.
I mean, you worry about, you're taking the brightest things. The dimmer ones may react differently.
Yeah, and that's definitely something that we want to test a little bit more. But so far, this is the best strategy we've come up with, at least at this point. But as we get more and more epochs, we'd love to be able to test things a little bit further.
Well, you take all the dimmer sources, and there should be more of them.
Yeah.
You're just doing differential metrology.
Yeah. And hope, the more and more we look at, the more likely something will be varying. But yeah, this is definitely something that we can push a little bit further. But for at least the initial pipeline of picking out the easy to find ones, this is more what we've been doing. So using this example, if this was a calibrator set, you just take the average of the normalized brightness for each epoch, so 1.04, 5, 0.97, and so on. And so if we had a third star, and I'll point out that these are all numbers that I've just made up. This is not any particular star from the data set. If we had a third star, just looking at it, initially you would say, OK, looks like random scatter. I wouldn't necessarily pick out any particular point as being discrepant. It all looks to be about the same for noise. But if I was to then divide by the normalized brightness, we get a very, very different picture. And you can see that most epochs seem to be hovering around 300, but then this third one really jumps out as being discrepant. And so by hopefully improving this calibration, we're going to be able to better pick out what's noise, what's actual variability. And so we think with this technique, at least with the checks that we've done so far, we think we've been able to improve the calibration from about 8% down to about the 2.5% level of calibration by basically doing sort of self-calibration based upon the brightness of sources within the images. All right. So when it comes to actually then picking out the brightness of particular sources consistently, we've had sort of two different approaches that we've been using across the group. One's been a sort of a clump find approach used by Hinju, and I've been working on a bit of a Gauss fitting approach. I will admit that Hinju's approach has been developed a little bit further than mine and seems to be working better than mine. So I wouldn't be surprised if her approach is the one that we use going forward, but I'm still tweaking mine to see if I can get it working. So I just want to quickly mention both ways that we're using for this to actually find the brightness. So what Hinju is doing is she first combines all of the data into one master image such that it has the best possible signal to noise. It gives you the best chance to resolve structures that are similar in brightness that are nearby. It gives you the best chance of finding faint objects. And what she then does is she then runs clump find on the total image. And so what clump find does is it takes a look at the intensities and basically divides up all the pixels and says these pixels are associated with this local maximum, these pixels are associated with this local maximum, and basically it divides up all of the pixels with significant flux and assigns them to some local maximum. It assigns it to some clump. Basically, it's like drawing borders on a map, that you have your capital cities and then you allocate space on the map to each of those capital cities. And so what we can then do is for each epoch, we can then go back and say, okay, these pixels are all associated with this clump, these pixels are all associated with this clump. Even if we have lower signal to noise and can't necessarily pick out those clump in individual epochs, we've divided the map up using our best signal to noise image. And so what we then do is then we look inside of each of these clump regions and we pick the one pixel with the highest intensity and say that is the brightness of that particular clump for that epoch. And then from that, we can then build up our light curves and search for variability. This definitely has some advantages that we are dividing things up based upon what's actually in our map. We're identifying clearly seen structures in the sub-millimeter. It's very clear-cut what pixels we're assigning to which source. The problem is by picking the brightest pixel in each source, is we're probably biasing our estimates of intensity a little bit too high. Because if you think about if you had something that was completely uniform and then add Gaussian noise, the brightest pixel is going to be the one with the highest amount of noise that just happened to get added. And so by searching for the brightest pixel, we're probably picking one that's been slightly increased by random noise rather than decreased. So we're probably slightly on the high side, but given the levels of variation that we're expecting to see, sort of 20–30%, we're reasonably confident, at least, that we can still pick out variability reasonably well. The second technique, the Gauss fitting that I've been working on, has been to first look at the literature to find the locations of protostars, and basically take a catalog of all the positions of protostars that are known. And then what I do is I take a roughly 10 by 10 pixel cutout of the data and then try and fit a Gaussian to that region. You can then take the peak of the Gaussian fit as the brightness of the source. The advantage of this is that you're using multiple pixels to inform how bright the peak is. And so you can smooth out the noise a little bit, so you're more likely to get the right peak intensity. You're not necessarily biased high. The problem I'm really having with this, though, is that we're picking where to look at these based upon catalogs, not necessarily based upon what we can actually discretely see in our images. And so I'm having a lot of difficulties with protostars not appearing strongly in the image, and the Gauss fitting instead a source to the side here, or a source to the other side in another epoch. And I'm definitely struggling getting the Gauss fitting to fit the source that I want it to fit consistently in an automated manner, because I really don't want to have to go through by eye and fit 1,500 sources every month. So still got some work to do with automation of the Gauss fitting. But if we can get this happening and we can see these nice Gaussian profiles, it'll be nice to smooth out the noise. It's just not necessarily clear that in some of the more crowded regions whether we'll actually see a Gaussian profile if the protostars are blended in with more diffuse emission. Either way,
About, I think it was Hyunju's technique.
Yep.
I know that when you run your algorithms on like a star forming region, there's a lot of other stuff that comes up, not just protostars. So how do you find just protostars and not all these starless things?
To be quite honest, we're happy. If we can find a time variable prestellar core, that would be awesome. So we pretty much just run it across and we see what we get. We don't think the prestellar cores should vary, but if it's in the data and it's varying, we'd love to know about it. So to be with the method, we're actually pretty happy if we get things other than protostars. But if it is the episodic accretion, we would expect the protostars would be the ones that are more variable. But we're happy to look at prestellar cores and protostars because we'll see what we can see.
Sometimes the cores are thought to be prestellar, and then somebody finds some very dim protostar in there. So some of the things you think don't have sources might have.
Yeah, especially the most deeply embedded ones. You might not see them until they go into a burst, perhaps. So yeah, we definitely love to, we're happy getting the prestellar cores with it. It's definitely an added bonus. It's something with my one, I'm actually tempted to go back in the catalogs and add in all the prestellar cores to make sure we're getting obvious localized sources. So once we...
When you're doing this to get your light curves, you are using some information about where, well, your approach is using information on where you think the protostars are. And the Calibration approach is just sort of finding the brightest thing in the image. But that's just very different from what people do in like supernova searches, where they take difference images and look for something that comes out of the difference image. So what's motivating the difference?
So one of the things by eye is we've been played around a little bit for the difference images. The biggest problem that we're finding is that there is some fairly large scale structure around the prestellar cores, and depending on how the JCMT was doing with chopping and everything else, we're finding a bit of variability in the larger scale structures. So when we do the differencing, we're having to be very careful that it's a particular source that is varying rather than the larger scale structure behind it, just because with the chopping we do have a lot of filtering issues going into the JCMT database. So the calibration of the large scale emission is hairy. I think is the best way I can describe it, just because we do have a lot of filtering issues with the JCMT. But we have tried it. We're at least trying to do it by eye. We're encouraging the team leads to blink through everything by eye, play around a little bit with differencing, but we haven't come up with a good automated way to do it to actually get at the sources themselves. So once we do have the light curves, we've got a couple different ways as well of checking to see if there's variability. This basically, I'm calling them an internal and external variance, but I have no idea what's the best way of describing these. These are my own terms. I don't really like the terms. So one way of looking for variability is to just take the standard deviation of the light curve. So this is a made up spectrum. I created this on my laptop a couple days ago to put into the talk. This is not actually a detection. I would love if I could see data that looks like this. So one way we could do it is you could calculate the standard deviation. You could look at, say, the 2 sigma standard deviation, which is the dashed line here. And then you could see the last one would be 2 sigma standard deviations away, and you could flag it. Another way you could do it is you could take the standard deviation of every point but the one you're looking at, because this one discrepant point is going to significantly increase the standard deviation. So if you take the standard deviation of all of these points, not including this one, this is actually the 3 sigma line, the dashed dotted line, and then you can see that that one really is discrepant. And so that's one variability filter that we're applying, is just looking at the standard deviation of a particular source. This is really great if you have one epoch where you started to see the variation. So if we're continually doing this and all of a sudden something goes into a burst, this is a great way to find it because you've got that one data point that becomes discrepant. The problem with this, though, is if you have catch it sort of in the middle of variability where you've got a slow curve, multiple points in burst. So if you had a spectrum like this, the dashed line now shows the 2 sigma standard deviation, and excluding just one of these points isn't really going to change the standard deviation. You're still going to basically say all the points are consistent with not varying, even though we can see a longer term trend. And so the second way we've been sort of looking at for variability in the data is to compare the points to the standard deviation of protostars with similar intensities. And so based upon the idea that most protostars will be in a quiescent phase and staying reasonably constant, that gives us a sense of sort of how good the calibration is. And so by looking at how the intensities are varying at a particular peak intensity, I could plot, again, the 3 sigma from the previous plot. We would then say, oh, something's going on here, flag this particular source for further follow-up. And so sort of an internal one of looking just at its individual spectrum to see if things are changing, and then more of an external one where we're comparing the spectra to similar protostars and how much they're varying to try and get slower, more gradual changes in the data. And so we have been trying this. And I'm very happy to report after a year, we do actually have one star which appears to be variable. That it does seem to be working a little bit. Then it was found in Serpens, so it wasn't found in my region. It was actually found in Hinju's region, which, again, she's got the more advanced pipeline at this particular stage. And so you can sort of see the large-scale flicker. So again, this is a little bit with the issues of chopping, trying to work out the large-scale flux with everything. So you can see everything still flickering, which you can sort of see why difference imaging could be problematic. But if you take a look at this one source here, you can see it very clearly brighten and dim. This is just one loop going over and over. So we see it brighten and dim, and that's it. We don't see it repeating. But we are fairly confident that this is our first variable star detected. It's got a bunch of different names in different catalogs. It's referred to as SM9, V371 SIR, EC53, or Source 7, depending on which catalog you look at. Yep. Yeah, roughly a 1-month cadence. I've got the full light curve on the next slide. So this is the light curve that what you guys are seeing. So we started off the survey, and it behaved normally, not doing anything. And then about 250 days in, it brightened by about 10%. We then got really excited, and then we realized that the sun was in Serpens, and we had to wait about 3 or 4 months before we could actually observe it again. And everybody was really tense because we were worried it was just going to be back down here, and we had missed it because the sun just happened to be in the constellation. But thankfully, it came back, and it was still bright, 20% brighter than it was before, and we're starting to see it slowly fade now. And so we got this really beautiful 30% variability. The similar calibrators of similar brightness you can see are all sort of within that 4%, 5% variability. Nothing at all like what we see. And again, it's about a 1-month cadence. The JCMT chooses when they observe. They were actually really good. There was so much good weather at the beginning, they started to observe slightly less than 1-month cadences. And they were using all of our time, so we had to tell them to just slow down. It's OK. You know, we want to wait and go 3 years, so don't use up all of our time early. And you can see if we plot the flux variation versus the absolute flux, that this one source really jumps out of most of our calibration sources. And what's really, really cool about this source, it's a class 1 source. So it's not quite the class 0 that we were hoping for, but still reasonably young. So what I'm showing here is, again, the light curve that we have observed. And then I've just folded it over again for a second phase. And the reason I've done this is that this particular source has been observed in the K-band before, and it's been known to be a periodic variable. It's not just episodic accretion where it goes through a burst. This particular star appears to have periodic brightening in the K-band. And in fact, if you look, K-band is about 543-day period. We're looking probably, if this comes back down, we're expecting it to be, again, a very similar period. That it looks like the sub-millimeter periods about the same as the visible. Although I would like to point out, when it's dim, we've got a fairly wide, 200-day flat region, whereas in the visible, it's actually fairly small, that it's varying for most of it. It's got a very small minimum phase. So we do see some very tantalizingly interesting differences between the sub-millimeter and optical, and so K-band at least. And so we're definitely very interested in continuing monitoring this source for the next 2 years and hopefully getting some simultaneous K-band observations to really see what's going on in the different bands.
If they're not simultaneous, if that K-band is repeatable, then you know what the K-band should have been doing.
Definitely. And I want to say, I think 1999, I think there was also further data early 2010s as well. But yeah, it would be real, just make sure at least it is still varying. It would be great to also see how close the maximum lines up to the K-band maximum, or if there's a phase offset, would be really interesting to see as well. So we think this is, so we're fairly confident this is a class 1 source. It could be class 0 if it's exactly pole on and we're looking down the outflow cavity, but it's probably class 1. It's known to have a physical binary companion about 92 astronomical units away. It's cometary nebula, signs of outflow activities as you would expect. And then, as I said, periodic variable at 2 microns seen in a couple different surveys. Now, the next bit is going to be basically complete speculation on my part, or at least, actually, I should say this is complete speculation on Doug Johnstone's part. I grabbed this slide from him, so if it turns out, we'll see what happens. But since it's got an 18-month periodicity, this means that we would expect something's happening on the disk in about 1 AU scales. That this 92 AU binary star is too far away. It would cause a much slower periodicity than this 18-month periodicity. So something interesting has got to be happening in the inner disk on sort of that 1 AU scale. So possibilities, maybe there's an unseen companion or some planet at this 1 AU scale that's driving this periodicity. Could just be other interesting things in the disk. But the fact that it's periodic is particularly interesting. If you do have another source, then the 92 AU source, is this a third companion? Is it stable? Has there been interactions? But we're still, as I said, about a year into the survey. We've got another 2 years to go. So definitely keep an eye out for this. We've got an early draft of this paper ready to go. So hopefully you'll see the early paper come out. And hopefully in 2 years, we'll be able to tell you a lot more about this source. And hopefully we'll have a bunch of other variable stars as well to tell you guys about. All right, so I don't have too much time left. So I want to quickly change gears and talk a little bit about the Orion-Eridanus Superbubble. So this is a project that's been in collaboration with Juan Diego Soler and Andrea Bracco. So again, some of the work I'm going to show is not necessarily my own. So first of all, what is a superbubble? So when you have a high mass star, you get significant radiation pressure, significant winds, and eventually a supernova explosion. All three can influence the gas around it and basically push the interstellar medium away and create cavities in the interstellar medium. And very picturesque supernova remnant from just one supernova. When you take a whole cluster of massive stars, the combined effects of their feedback can create very large bubbles. These bubbles can become hundreds, if not thousands, of parsecs in size. And this is what I'm going to refer to as a superbubble. So it's basically a bubble created by an OB association rather than just a 1 or 2 O stars. So if we look at the anatomy of a superbubble, we've got our massive stars at the center. We have the gas in the galaxy around. And then in the very center of the bubble, we're going to have low density, very hot plasma, million-degree plasma, X-ray emitting gas, very low densities. This high pressure of the interior basically causes the bubble to expand. It sweeps up all of the gas from the interior into a surrounding shell. The interior of the shell is going to be ionized by the massive stars. But if the shell is thick enough, the exterior can still be neutral if all the ionizing photons are absorbed by the inner part of the shell. However, if the shell isn't thick enough, then some of the ionizing photons are going to go through the shell. And if you have any clouds just hanging out around the outside of the bubble, those are also going to get ionized. So you can get H-alpha features outside of the superbubble that are caused just by the ionizing photons leaking through the bubble wall. Similarly, if you've got a whole bunch of massive stars inside your superbubble, you're going to get subsequent supernova explosions. Maybe you had some leftover molecular clouds that are still being dispersed. And so it's easy to create additional nested shells within your superbubble, shells that can expand and then re-energize the larger superbubble wall. So it's quite possible to get H-alpha structures inside of your superbubble and outside of your superbubble. So if you have really great data with lots and lots of features, sometimes it's very tough to tell where is the actual wall of the superbubble. Because it's quite important to understand the evolution of these bubbles, how quickly they're expanding, what the shapes are, to actually be able to identify where that pressure-driven wall is versus what's interior shells versus what's just illuminated features outside. So this is the particular superbubble I've been looking at. This is the Orion-Eridanus Superbubble. It is generated by the nearest active high-mass star-forming region, the Orion star-forming region. You can see the A and B molecular clouds right in here. Its name comes from the fact that it spans 2 constellations, the Orion and Eridanus constellations. And it is huge in the sky. Because Orion's so close, I want to give you guys a sense of scale. I'm going to show you guys the stars of the Orion constellation. This is an absolutely massive bubble. This is tens of degrees in size in either direction. We're talking 1,000 square degrees on the sky. That if our eyes were sensitive to H-alpha emission, this would be amazing in the night sky. It's a little bit unfortunate that our eyes are not actually H-alpha sensitive to actually see this sort of structure in the sky. Other thing I should point out with this is you can also see the galactic plane running across the top of this image. So a lot of those structures are just in the galactic plane at further distances. So we want to know, what is actually the bubble here? It's so close, we see all of this beautiful detail, but what's actually the bubble? What's actually the bubble wall? So when I started working on this as a grad student, my first guess was, well, maybe it's a very skinny bubble. And so what I basically did is I said, well, let's take this bright loop here, Bernard's loop. Let's say this is the edge of the bubble, and let's just trace along features until we get to the end, and then trace along features back. And all of this extra stuff, let's just say, is ionized material outside of the bubble. So we get a very skinny bubble. It's so skinny, in fact, that it actually causes problems. That as superbubbles expand, you do expect them to become elongated as they start expanding into lower density gas. That they start realizing there's less gas farther away from the galactic plane, so they preferentially expand away from the galactic plane, creating chimneys. The problem is that this superbubble isn't big enough to really have seen about more than a scale height, that it should be reasonably spherical, given how big it is. The other problem as well is, depending on the distance to this end versus this end, you actually find that the superbubble might actually be parallel to the galactic plane, rather than perpendicular and blowing out. And so this caused us to come up with lots of fun ideas about what could create such a weird, elongated bubble. Maybe it's magnetic fields channeling the superbubble. Maybe you have a moving source. There was a great paper by Bowie et al. Talking about blue streams, of how towards Orion they see evidence of older B stars closer to us and then younger and younger moving towards Orion. And so maybe there was this propagating star formation. And so if you had a supernova go off, moving source, another supernova, and moving source, another supernova, maybe you can get this nice cigar-shaped superbubble as all of the bubbles merge into each other. However, it was also recently suggested, well, maybe this isn't actually the bubble wall. Maybe this is the bubble wall. Maybe the exterior H-alpha features are the bubble wall, and everything inside is just nested shells. It's recent supernova events, recent star formation that's expanding, and it's going to re-energize the superbubble. And so we'd really like to know, which is it? Is it the big bubble, or is it the smaller bubble? Is it more spherical, and this is more consistent with expansion just in the galactic exponential atmosphere, or is it a really skinny bubble and we need magnetic fields and moving sources and everything else? And so we've turned to the Planck data. That Planck obtained polarization data, pretty much all sky, which is great because it's such a big source, we almost need an all sky survey. And from the polarization data, we're able to derive the magnetic field orientations. And the nice thing is, with a superbubble, as the superbubble expands, you would expect it to sweep up the magnetic fields into the shell. So you would expect to see enhanced magnetic fields in the shell of the bubble, and you would expect to see the magnetic field running roughly along the edge of the bubble wall. Any material that's outside of the wall that's just illuminated, it hasn't been swept up, it should not have an enhanced magnetic field. The magnetic field shouldn't necessarily make a nice bubble shape. Same thing with the interior. If you've got something, bubble inflating into the interior, it's just expanding into the hot plasma where there's very little magnetic field to sweep up. So we'd expect, again, interior features should have very little magnetic field. And so our hope is, with this magnetic field, is we should be able to spot where the actual shell is. And so the lines here show the magnetic field, and you can sort of see lots of little vortices, but you can sort of see one feature just extending down from the plane, turning over, turning back up, and you can sort of see, maybe if you squint at it, a bubble feature in the data. And I've got a few other slides that show it a lot better. So what I'm going to do is I'm going to show you the H-alpha, And I'm going to show you the exact same region of the sky in all of the images. So when I blink back and forth, it's going to be all aligned. And what I'll point out to watch for is the big bubble model uses this outside H alpha feature here. So it's sort of between the edge and this longitude line. But the small bubble goes along Barnard's loop and then comes down this way. So the edge runs very close to this intersection of the coordinates. And so if you're looking at other slides, watch if the bubble goes through this coordinate edge or if it goes over here. So this is the polarization fraction as seen by Planck. So the lighter it is, the more polarized it is, the more likely that we have a high magnetic field, and thus this is likely where the bubble edge is. And so you can see this really nice bubble going down, arcing around, and coming back up. And you'll notice where the edge is. It's out here. That it looks like it's a big bubble that the polarization is tracing. You can see it even more clearly. This is showing the gradient of the polarization directions normalized by the polarization fraction. Black means it's more uniform. So again, you can see the bubble running down, cross, and going back up. And I've actually got the H alpha coming in and out. And you can see how beautifully it lines up. Like just down here, that's just absolutely beautiful how closely that aligns. And again, you can see it's running out to the larger bubble. So it's very, very conclusive from the Planck data that it's the larger bubble that's right. It's the more spherical bubble. We don't necessarily need magnetic fields and fit moving sources. It looks like just expanding in the galactic exponential can account for most of the structure of this particular bubble. Magnetic fields could still do something. Moving source could still do something, but it doesn't have to be the dominant effect. I should also mention that from the polarization data, we can also get a magnetic field strength out from the Chandrasekhar-Fermi method, but we're currently working on that right now. We don't actually have any measurements. So stay tuned. Hopefully we'll have a paper out in the fall with the full magnetic field analysis to say how strong it is, whether it's dynamically important, as well as the full paper writing up what is actually the size of the bubble. That's pretty much all I wanted to say. So I talked a little bit about the transient search for protostars, JCMT large survey of 8 regions, taking an image every month for 3 years to get both the time variable structure, and we're also going to get some of the deepest images ever when it's all done, at least of these sources. We've got one variable source, and hopefully we're going to get many, many more to come. And then with the superbubble, we've been looking at the one caused by the Orion star forming region. We've been able to conclusively show that it is the larger, more spherical bubble, that it seems to be consistent with the bubble wall, and we're hopefully going to have a good analysis on the magnetic field strengths and how dynamically important that's going to be coming out in the fall. So I'll stop there. So if I went a little bit over time, and if there's any questions, I can open it up to the floor. There's definitely been some rough estimates done earlier based upon the different expansion speeds, what radial velocities you're seeing, the expected mass through everything. We haven't redone it for the particular larger bubble. It's something we probably should take a quick look at for the energy density, but we haven't taken too close of a look since the initial papers that came out. I think part of it is just figuring out what the actual expansion velocity is. Again, there's just so much detail with all the features that it's slightly less than trivial. But we'd love to be able to compare the sort of kinetic energy to the magnetic energy and see the importance of everything.
So so what's the thickness of these superbubble layers? How many estimates?
There's definitely estimates. It's not, they're actually, goodness. 400 parsecs, this is, I think, 20 degrees, so maybe half a degree at 100, half a degree at a few hundred parsecs.
About 30 parsecs.
Yeah, I was going to say it was sort of parsec scale thickness, but I'd have to. I'm sure we've measured it out, but I don't actually remember. It's actually reasonably thick. The density increase in the shell wall isn't that substantial. We think with the magnetic fields that it's mediating the shock a little bit, so it actually, you don't see that much of a jump in the density towards the shell thickness. So it's probably only, it's at most like a factor of 10 density increase. So it's still, yeah, you're probably talking, parsec to 10 parsec thickness.
Now that you mentioned density, is there a particular power law in the shells of the bubble with density falling off?
I don't think we have that great of an estimate. That usually for the density, I think a lot of it comes from assuming it's an ionization front, assuming it's in pressure equilibrium, and then just getting a density. I don't think there's been much work done. I think the biggest problem is knowing what the line of sight depth is. That I think that's really dominating the uncertainty in the density. So there are definitely order of magnitude density estimates. I think we're talking 1, maybe 10 particles per cubic centimeter, order unity particles per cubic centimeter. But I don't think we have a great consensus of how the density actually changes across the bubble walls themselves. I'll point out as well, if you look at the H1, there's this beautiful H1 shell that lies just below here as well. So potentially you might expect temperature gradients and density gradients, but I don't think there's been any particularly good estimate of how the density changes within the shell wall.
So if you have a bigger bubble, then what do you think generates that striking architecture at the top?
Yeah, in Bernard's loop. So Bram Oschendorf was the first one to suggest that it was a nested bubble. You do have the Orion star forming regions here, so it's possible with all the molecular clouds with the Orion region. What we're seeing is a new generation of stars kicking off, blowing away some of the molecular clouds, supernova explosions, basically creating new remnants. It's interesting a little bit that we lose this side of the bubble. If you look very faintly, you can actually see it close, which is why Bram suggested it was a nested shell. You actually do see it as a full sphere if you look very carefully. Why that's particularly so, I know Bram had a few ideas about what might cause that side of the bubble to disappear more. It could just be as well where the stars were in the molecular cloud. You've just pushed more material this way. Could be something to do with the galactic plane. There's just less material this direction. It could be an erosion. You've got all the hot plasma here. You might have an erosion of that side of the shell interacting with the with the interior of the bubble. I know that he had a few ideas about why you've lost the southern side of that arc, but you do see it as a full sphere. So I think the generating source is just the Orion star forming region. It's just a new wave. And you're just getting supernova explosions within this larger structure. Because you definitely see multiple epochs of star formation within Orion. You've got a bunch of different clusters, 10 million years, 3 million years. It's possible that one of the more recent ones have kicked on and started blowing out some of that material to generate a new shell. And hopefully, eventually, this shell might catch up with the superbubble, hit the superbubble, re-energize it, dumping energy back in and causing an increase in the expansion of the larger bubble.
Just
Yep.
one quick thing about the shell again. So do you have any estimate for how long these things are stable for? Like, do you think it's stable for kind of scale? The shell, I mean.
It should be possible to estimate that. I don't know offhand what's been done with that. I know there's definitely been some papers about just with the thermal instability of just the hot gas inside of losing the shell material back into the superbubble and quenching it. You would expect things like the Rayleigh-Taylor instabilities to kick in. I know there's simulations that's been done that have looked at when it kicks in, but I can't honestly tell you offhand what it is. But I'm fairly confident the simulation that there's been plenty of simulations that have started to see when the Rayleigh-Taylor instabilities kick in and start dissipating it. But I think it might also depend a little bit on how your driving source, how powerful it is, and how it just quickly it kicks it out to become a chimney. Because we definitely see signs of chimneys elsewhere. We see other larger bubbles kicking out towards the galactic halo. This is one great way to actually get hot gas out into the galactic halo with these larger superbubbles. All right, I think that is all the questions then. So.